So let's go directly to our second speaker now to have a bit of a contrast, to move a little bit perhaps along the arrow of time. Colin Normane is a good old friend from Johns Hopkins, a friend and perhaps co-conspirator in the days and months and years leading up to Hubble's launch. Colin is a senior professor of physics at Johns Hopkins and across the street a senior astronomer at Space Telescope Science Institute. He hails originally from Melbourne, where he took his undergraduate degree, then on to Oxford as a Rhodes Scholar, where he took his doctorate. He's taught at a number of places, but for the past 20 years or so, he's been at Johns Hopkins. He's also got an incredible number of papers, well more than 200 in the published refereed journals. He's done a wide spectrum of astrophysical work with objects that seem to be explosive, whether they be accretion disks of holes or gamma ray bursters or a wide variety of... I remember reading some of his earlier papers on interstellar masers when I was coming up to the system here in the 1970s. So let's not hesitate at all and go directly to our next speaker. Please welcome Colin Normane from Baltimore.
So, it's on. Great, but I need it up here. Thanks. I need to push the buttons. That's great. Thank you very much, Eric. Those were great days. Incredibly character-building days when we had to explain to a Senate review panel why Hubble didn't work. And then we had to, in fact, ask for, they said, well, how much will it cost to fix it? And we said, only $1 billion. So it was quite fun. Yep. I'm trying to explain something in the next half hour about galaxy formation and evolution. And I thought I'd show a galaxy first. So here's M83, magnificent spiral galaxy. Our galaxy is quite like this, but it has a little bit of a bigger bulge and somewhat more open spiral arms. But just to set the scene, where if we were living here in this galaxy, we'd be out here on the edges of the galaxy, around about 10,000 light years out. And in the lifetime of this galaxy, our sun would have rotated around something like 30 times. Okay. The rotation time is 300 million years, and the age of the universe I'm taking is nominally 10 gigayears. And the time, let's just look at a little bit at this rotation. So I said 300 million years to go round, and then think if we take a conservative estimate for the time with which we have been doing, what we might call modern science, and we would say it was very, very conservatively 10,000 years, then we have only rotated about to there. So we're this tiny speck of dust on the edge of a beautiful galaxy, and we're trying to understand something like this, the entire universe. And as Frank has beautifully explained, there's many magnificent problems about this. I'm going to tell you some things that we have actually found. But I should also say that when I go out the door in the morning sometimes, and this is echoing the 5% of baryons in the universe, my children say to me, Dad, why are you even bothering to go to work? Because you're only working on 5% of the universe. So anyway, we start with the Big Bang. The universe is extremely hot, and then as time goes by, it cools. And it cools from a hot plasma, electrons and protons, down to a nice neutral plasma, and this occurs at about 1 million years. And then there's a long time called the Dark Ages in which nothing happens. Nothing at all. There's no star formation, no galaxy formation. It's just a big ocean of neutral hydrogen. And telescopes are being planned to try and observe this, but if nothing's happening, it's really difficult. So then after some time, at what we call probably at about a redshift of 20, and I should say what redshift is. Redshift is essentially the amount that the wavelength of a spectral line, the wavelength of, say, the hydrogen line at 21 centimeters, or any other line that you like to think about in the hydrogen atom, is shifted. So the relative shift in the wavelength relative to the center of the line is the redshift. So at a redshift of about, let's say, 20, and I'll show you simulations of this, the first stars begin to form. And then, and why do they form? They form because there are fluctuations which have been imprinted in the universe from the very beginning, which grow slowly over time. They grow slowly over time because the universe is expanding. If the universe wasn't expanding, these fluctuations would grow extremely rapidly, but because it's expanding, they grow slowly. And why we know so much about these fluctuations now is from the beautiful work of the satellite called WMap, which managed to measure the level of fluctuations and deduce many parameters of the cosmological parameters of the universe from looking at this surface here where the universe recombined. Okay, so you're looking at fluctuations here and measuring them, and they've been imprinted from the Big Bang, but this is the first place, at least currently, that we can measure them using radio telescopes. And these fluctuations are allowed to grow from about here onwards, and they grow sufficiently to become nonlinear and form the first stars, then those stars, and then the first galaxies. And then the general cosmology that I'm going to talk about, galaxy formation, comes in. And one of the major observations that I'm going to talk about come from the Hubble ultra-deep field, where we can begin to see galaxies, interesting properties about galaxies, not just isolated properties, but statistical properties about galaxies, now at about a redshift of 6. When Eric left Baltimore in 1992, this was a very unfortunate event, of course, because he used to sit next to me at operatic meetings run by Riccardo Giacconi, and he would write down, I thought he was working on something else, but he would write down everything that was going on. It was most interesting. Later, some of it appeared in a book. I'm losing this. Okay. So the Hubble. So when Eric left Baltimore in 1992, no one would imagine that we could get what's called the luminosity function of galaxies, for example, at redshift of 6, which is where the Hubble deep field goes out to, the Hubble ultra deep field. And so I'm going to proceed reasonably rapidly and tell you about how galaxies form and evolve on the basis of some of the observations and some of the simulations. This has been gone over by Frank, and it's slightly blurred. I don't know why, maybe because our understanding is a little bit blurred. But dark matter is about 30% of the universe. Dark energy is about 70%. I think the guys don't like me up there. First, I'm going to turn off the laser pointer. Wait. Was this meant to be connected? Okay, I'm going to take this off and just swap it, man. Well, you see, something is happening. All right.
Here, we'll switch to the red one.
Yeah, whatever you like. Give me that one.
Oh, the red one. He's going to go to the red.
Very good. It's on now? Yep. So you can see why my children worry about this, because that little band there is just, that band there is 4% of the universe, and the rest we know little about. Okay. What? This is ridiculous. I've never had so much trouble. Do you think it's because I'm in Boston? You know, my children said, "Don't even go there, Dad. The Red Sox play there." Okay. So a long time ago, when the universe was about 1/20th of its current age, a very interesting event occurred. Probably a massive star collapsed, a central black hole was formed, and an enormous pulse of energy in gamma rays called the gamma ray burst, lasting about 10 seconds or so, was sent out from this object. And we saw it, or at least the observers here on Earth, and with the satellite orbiting the Earth, saw it last week. And so this is the formation of a black hole of the order of, a solar mass, maybe it's 10 solar masses, in the region that I'm talking about where galaxy formation began, and that's about redshift 6. And this is an amazing new discovery. We think that black hole formation like this, with probing the universe with gamma ray bursts, and looking at these black holes forming at redshift 6 is going to become relatively easy, and one can see them even out to redshift 10 with current instrumentation, and I think it's just a matter of searching for them. But this is a relatively, we get a new discovery in astronomy about every month, but this is the one from last week, relevant to this subject, which is really quite interesting. And I submitted the paper about it on Sunday night. Okay, now the universe is neutral. It's basically until something happens, some stars form, some galaxies form, then it's essentially doing nothing. So stars form, galaxies form, and the regions around these stars and galaxies, and this is an artist's impression, begin to ionize the medium. And we know today that the medium's ionized, and from the WMap results, which have enormous error bars, we know that the universe was ionized somewhere between a redshift of about 10 and 20. And it goes like this. The physics of actually understanding how to do the ionization calculations in the universe is very difficult, even with current large computers, and is a subject of much current research. So we think we can reionize the universe with the available stars at about a redshift, around 10-ish. The next thing that I wanted to talk about is how we measure the acceleration of the universe. We do that currently using type 1a supernovae, a special sort of supernovae associated with a sort of a standard mass compact star called a white dwarf. And we look very carefully, or people look very carefully at images of galaxies on a routine basis and find little things here, like supernovae. And you'll see why we need a space telescope. You'll see here, this is before the supernovae, then afterwards, before, afterwards, etc. If you don't have a high-resolution telescope such as Hubble, then this supernova gets embedded in the general light of this object, and there's no other way currently to find supernovae. So you need Hubble or some better version of Hubble to find these supernovae. And there are plans made to fly, very expensive of course, missions in order to get many, many supernovae and try and understand the acceleration of the universe. And this is the diagram that one has in one's mind about what these what we can learn from studying these supernovae. The universe is our current... Oh, I can't believe this. Why is this happening? I think it's a Boston conspiracy. I'm never coming back. Okay. So, the universe probably does something without a lambda, without a cosmological constant, the sort of thing Frank talked about that is small but important. It would do something like this. But with the cosmological constant, you can see that it starts from the Big Bang, decelerates, and then begins at very large distances to accelerate. And one can get images, one can get determinations of the acceleration in the universe by plotting these type 1a type 1a supernovae results and analyzing the expansion. There are many other ways to determine the expansion of the acceleration of the universe, but they are not quite as mature as the supernova type 1a results. Okay, here's a magnificent spiral galaxy from the Very Large Telescope at ESO in Chile, and this is NGC 4565, and you can see dust lanes, a beautiful bulge, etc. But when we look at the dynamics of this galaxy, it is observationally, unambiguously determined that this is just a small fraction of the dynamical mass. And you then, let's say, if you go from about here and go out by a factor of 10 in both directions, then that will be the radius of the actual galaxy, and that is all made of dark matter. So again, we're just seeing the froth on the dark matter distribution, even with such magnificent luminous things such as this wonderful edge-on spiral galaxy. Now, I mentioned the Hubble Ultra Deep Field, and this is it. We're looking deep into space, and the very faint objects are little galaxies forming at up to redshift 6. And there are many interesting things about this slide. I'll show you a couple of details. The first is that the galaxies are often disturbed and distorted, okay, as you can see. And but you can begin, in some cases, to see significant structure. Okay. What one learns from this, and one's learned the same thing from many other calculations. So number one is that many galaxies are disturbed, distorted. They look like they're interacting and colliding. And it does look like the great models that have been made over the last 20 years of cold dark matter halos with appropriate gas dynamic physics, where it's sort of a bottom-up approach where you make the small things first and they build up and make the bigger and bigger galaxies. This looks like it has some significant validity if we look at all the merging and interaction that's going on at high redshift. There are some well-known, at least in the field, potential problems with this, but I won't go into them at the moment. But generally speaking, the overall framework is reasonable. Okay. The star formation history of the universe is interesting. Previously, one thought the star formation, and this is time, and this is sort of star formation. And one thought that it went up and then came down. But it looks like there's a lot more star formation at early times than we previously thought. And this is going up to something like redshift 6. So here's the Big Bang, the dark era, the Milky Way's forming about here, our solar system's forming, life, etc. It's a bit like Eric's slide. And here's the star formation history of the universe. So it peaks, if it peaks at all, it peaks early. And this has been a big change in the last 15 years or so, to realize that many things happened relatively early in the universe. Now, locally, we see many examples of these colliding and interacting systems. Here's an optical image of the antennae where the two galaxies are colliding. There was a great and classic paper written by Alatumre from MIT explaining this in detail, and then he generalized it in a really profound intellectual leap that all galaxies may be made this way, that you're colliding two massive spiral galaxies here, and this is the central region of these things with all sorts of blue stuff, luminous blue stuff here, where star formation is going on. And this is the mode. Think of this as pretty much the mode by which all galaxies are forming. This is the very central regions where one's got a luminosity in this object which is enormous. It's not quite quasar-type luminosities, but it is enormous, and it's all coming from star formation rates where you're forming 100 solar masses of stars every year. And in this one, this is an X-ray image of such a region, a central region of where you're forming 100 solar masses per year, and this is from ARP 220. And there's most likely a black hole and a black hole which is being fueled at the center, but much of it is being obscured in the optical anyway by this by the large amount of gas in the region. But this is X-rays, so this is very hot gas, and enormous super winds come out of the central region of these colliding and interacting galaxies and pollute the intergalactic medium with metals and pump in energy and reheat it and give substantial amounts of entropy to the medium. This is another one, NGC 1569, which is again a diffuse small galaxy, which we see locally, starbursting, but it is typical of what we would see if you look carefully at high redshift. And this is the Chandra Deep Field, which I had great pleasure working on for a while. And this is an X-ray image of the sky. So I've been showing you optical images so far, but this is taken in the X-rays. And if you add up all the light from these active galaxies, mostly active galaxies here, there are some galaxies, very faint objects, which also emit low-level X-rays. But if you add up all the light from this, then pretty much this explains the X-ray background of the universe, so that a long-standing problem is the nature of the X-ray background was solved by these observations using the wonderful Chandra X-ray telescope, which is really run in Boston here at MIT and Harvard. What else can I say? In this slide, there are many this is covered with black holes, supermassive black holes, fueling the activity here, and there are galaxies around every black hole. But there are many buried quasars, and I'll come to that in a sec. In fact, right now. So let me skip a slide. Chandra observations are in the X-ray, Hubble observations are in the optical, and Spitzer, the great new infrared telescope, obviously operates in the infrared, but this can see deep into regions where there's enormous obscuration in the optical. So we're looking at active galaxies and quasars, so the region around black holes, using Chandra observations. We see nothing with Hubble, and yet they're coming out in the infrared. And this is the basis for what people now believe to be the claim that many black holes in the universe are hidden, and that there's a substantial, in fact most, in some claims in the current literature, most black holes may be hidden, and therefore we've miscounted the number of black holes in the universe quite considerably, number of massive black holes. I'm now going to show you some simulations. These are the biggest simulations ever done. I wanted to bring an IMAX movie, but then I tried it out again on my children, my teenagers, and they said, "Dad, you can't show an IMAX movie on your laptop. Why don't you get another one, right? A super new Mac, G4 or something." So I'll do that later, right? So 500 megaparsecs is the scale here. I'm starting at redshift 18, and there are fluctuations imprinted. Okay, so if I go reasonably quickly, so I'm just doing 4 per shot. So this is the large scale. Then I go quickly, and I see the structure of the universe has already developed, the large-scale structure, by redshift 0. And what I'm showing you here is the dark matter structure of the universe. Now I'm going to go to a 30 megaparsec scale, so this is much, much smaller than that large-scale structure, and you'll see quite remarkable things. So I'm redshift 18. I begin to see little things here, but then by redshift 10-ish, then I begin to see quite significant structures. You can see how stars would be forming, galaxies are beginning to form, clusters of galaxies form at the intersection of filaments, And then as I'm coming down now to redshift 0, this is about redshift 3, then you can see great clusters are forming. Certainly the cosmic web is well in place, or getting to be well in place, and now at redshift 0 you see it. And you can go to even higher resolution. I think there's 10 million points in this simulation. It's run by the Millennium Simulation guys, and I think Volker Springer, who was here, is the first author on this. Okay, so I think we've only got half an hour to go, I believe, so I think I'll just wrap up. We're trying to make galaxies that look like this. Okay, this is an infrared image of NGC 7331. So you can see that there's enormous complexity in here, which we're going to get onto later in the series. This is the central region of 7331, and then there's dust lanes out here, molecular clouds, all sorts of molecules in molecular clouds, star formation occurring in the spiral arms of this great galaxy. And many of the processes which produce the metals, which then go to produce the molecules, etc., are occurring quite obviously in beautiful structures in these vast spiral galaxies. And as this series goes on, you'll be able to essentially learn a lot more about the processes here and decide, things like, is life likely in such magnificent things all over the universe? Remember that there's, in 1990 again, we knew no planets around other stars. We now know somewhere between 100 and 200 extrasolar planetary systems. Remember also that there's 100 billion stars in our galaxy and about 100 billion galaxies in the universe, so that the number of possibilities is quite significant. And then this is NGC 891. This is a galaxy which is quite similar to ours. It's mostly dust, mostly shrouded by dust. It's got wonderful energy flows going up and down in the system. And one needs, in order to understand galaxies, one needs to understand the inextricable relationship between the star formation processes, the feedback that are going on from star formation processes. In the very center of such galaxies, there lurk black holes. One needs to understand how the energy input from black holes affects the galaxy formation processes itself. And so there's much to be done, as well as understanding the enormous halo of dark matter around this system, and then the vast space, smoothish space, in which it's embedded, which is essentially dominated by the dark energy. So I think we'll stop here and have a good panel discussion. Thank you very much.
Not sure if it's on. There it is. Okay. We're going to take a 1-minute break for you to get up out of your seat and seventh inning stretch in place. Don't leave necessarily, because the panel discussion for many people is the highlight of the evening. So we'll form the panel at this point and be back with you in 1 minute. All right. The way I run this panel usually is to try to break the ice by getting the two speakers to dialogue with each other a bit, though just for safety's sake, I'm sitting in the middle here. But the idea here is to try to, again, show you a little bit about what the scientific method really is like behind the scenes as you peel the veil and listen to two of the world's leading scientists talk to each other about truly unsolved problems. If you really be honest, and these guys are honest, for sure, that we don't have a good feeling for a number of issues that have been raised this evening. And that's going to be the point that I make initially here as I get my first licks in here, and then we'll eventually involve the audience in a larger dialogue. But I want to pose something of a general nature to both Frank and Colin that kind of bothers me in the world of submicroscopic physics as well as the macroscopic domain. And that is to say, when I was coming up through the system down the red line as a student in the 70s and 80s, taking courses with like Schwinger and Weinberg and all that, there was this great feeling of the submicroscopic realm that there was this standard model, And we felt in the 80s that we really were on the verge of realizing Einstein's great dream of unification of the forces and whatnot. And now I wonder, but don't answer this yet because I don't want you to answer me, I want you to talk to each other. I wonder, as I teach my kids, my students and whatnot nowadays, whether some of that excitement that we had in the 80s to realize the great dream of Einstein, unification of the forces, has receded a bit. And in the same, before you answer that, the same token, by the same token, because they're related, we had the feeling in the 80s of the kind of standard model in the universe. Yeah, we did know there was the dark matter issue, but we kind of used to say, well, we're off by factor 3 here, we're off by factor 10 here, and, you know, if we're losing an order of magnitude in astronomy, maybe it will kind of go away. We realized the dark matter problem in the 80s wasn't out there among the public, or certainly not the media, our friends.
Yep.
And now we have, this notion that the standard model of cosmology is I'll say it, it's plagued by not only a serious dark matter issue, but a dark energy issue. And one of you said it, I guess you said it. Your kids say, you know, we're working on. That's what the humanists say to me in my course. They say you're very confident. You say, oh yeah, it's dark matter. Oh yeah, it's dark energy. Oh yeah, it's we're gonna but we really are are we not? Let's put it a question. Are we not? And talk to each other in a bit of an embarrassing situation that might be a little like it was 100 years ago after the physicists had passed through the 1890s when they thought everything was wrapped up, but before relativity and quantum mechanics was underway. A situation where we really, from the humanist point of view, from the non-scientific scientist point of view, the impression is that we're kind of groping here. We don't have a good handle on the inventory of the macroscopic domain, and are we not receding somewhat from the enthusiasm and hope to achieve Einstein's great dream that we had 20 years ago? Talk to each other a little bit about this in terms of whether or not this bothers you as it bothers me and bothers the students I teach.
Nobel laureates can start.
I see.
If I understand the question correctly,
not a question.
I think you're showing your age. That's all.
All right.
Well, I think it's at least as exciting as it was in the 70s. In the 70s, we had a tremendous success. We wrapped up the structure of ordinary matter, really. And that's a historic achievement that thousands of years from now, if there are still humans or whatever follows, people will look back and say that was a remarkable century.
We haven't unified the forces of ordinary matter.
Well,
have we?
No, but 25 years ago, you couldn't even ask that kind of question. I mean, people said, people refer to this as Einstein's dream, but Einstein's version of it was so primitive and so wrong that it's silly to talk about it in the same context as today's conceptions. Today, I can draw these curves with actual numbers that would tell you what it would mean to have a unified theory. What are the quantitative consequences? And it's not just a dream. It's something that is very tangible in terms of predictions, in terms of expectations for the future. So, in a sense, I know the feeling you were referring to, which I think is widely shared, is that there was this tremendous success, and we're never going to be able to live up to that again. But I don't think that's correct. I think we've had a tremendous success, no question. I, of all people, don't want to understate it, but it's enabled us to pose questions at an entirely different level now. Entirely different.
Do you agree with Frank?
Yeah, I think it is a matter of description of level, actually. So that really was very fine to understand ordinary matter. But I suspect that the great adventure lies ahead in understanding the real mysteries of dark matter and dark energy. It may well be that dark energy gets ticked off as the lowest supersymmetric particle, but I'm not sure this will happen. Nobody is sure. But the dark energy is still going to be there, I think, and for some very considerable time. And I suspect the structure, we've just got a crude model of dark energy, and we're attempting to describe it by this famous equation, P equals minus rho c squared, where the minus should confuse any high school student. But that's probably incredibly crude in terms of our description of dark energy. And, you know, it's a bit like, I think in 1,000 years, I think Frank is right that the QCD, etc., will hold. But I suspect our understanding of dark matter and dark energy, how they're related perhaps, or what they do to the universe, and this great concept that's emerging of multi-universes, our knowledge of this and our understanding of this will look primitive, and the great adventure is to get out there and, you know, find out what's the truth.
Yeah. But I just to contradict myself and you.
Yeah. Oh, that's good. Now we can have a discussion.
I think there is, however, as I was alluding to in my talk, the real prospect of a retreat from the most ambitious dream that we'd be able to predict all these parameters.
Yes.
And, well, that's coming as something of a shock. But in a larger historical context, it shouldn't, because it's not the first time this has happened.
But is it not only...
Once Kepler thought that he would be able to understand the shape of the solar system, why there are planets at particular distances. Yes. Now we know that was an unattainable dream, that there are solar systems of different sizes and shapes.
But is it not just a retreat? Is it also not an embracing, it seems to me, of more and more ideas that are beyond the realm of testability?
I haven't given up.
Universes. No. Yeah. We mentioned multi-dimensions. Nobody's mentioned strings, thank goodness, yet.
No, this is where it came from.
Are we not hanging our hat in physics on an increasing number of issues that are beyond the realm of testability?
Well, I
hope not.
If they were really beyond the realm of, if they really beyond the realm of testability, I wouldn't be interested in them. No, they are testable. It's hard. We've done the easy stuff, but we have to be patient. I'm really very hopeful that the LHC will break through and into this new world of supersymmetry and you know, the ideas about unification and supersymmetry that I showed.
Yes.
We worked out in the early '80s, and we've just been waiting for this damn machine to get built.
Some evidence.
So it's not that the ideas aren't testable. It's just it's hard, but I don't think that's a reason to give up hope. We know that in astronomy, in cosmology, there was a long dark age, not just in the early universe, but in the period between the discovery of the microwave background in '64, I guess, and decades of people trying to find some evidence of structure in it.
Yes.
And not doing it trying harder and harder and harder. And then the Kobe satellite, which I guess was a 95 or something, 90, broke through, and now we have a richly detailed picture of the microwave sky of these anisotropies, and you know, we can justify the sort of simulations you show that they have some credibility. This is really how the structure emerged. So sometimes it's the progress is fitful, but I don't see any. I'm very optimistic about the future. I think
Let's open it up now a little bit. We've got two right fellows. Laura is over here with a roving mic, and Sherry is over there with a roving mic. So I see a gentleman right here. Sherry, you can come up to this man here. It's 8 o'clock position.
I just had a question.
Wait for the mic.
Okay.
so we can all hear.
By the way, if the SSC hadn't been canceled, we
don't
wouldn't
know.
have this. We'd already be there.
The revenge of the sea students.
Right.
We won't explain that.
Yeah, the C minus.
Images from Hubble. I understand that they almost didn't do the deep field imaging because there were some that suspected there were no stars or galaxies that far back in time to image. And they almost didn't do that. But they did, and they discovered that there were very distinct images in the far field projection. Now, are they now going to do longer exposures on Hubble to go back further in time? And what are the structures of the galaxies that they found that far back? It's hard to see from seeing the images whether you're seeing spiral galaxies that far back or you're seeing dwarf galaxies.
Yeah, that's a good
and do
question.
they have any structure way back in time? And how far back in time is that?
A lot of questions. So let's see. Yes, it's certainly true that I give up on this. So some theorists said that star formation, galaxy formation would occur late. These are the.
Don't move your left hand.
These are the same guys who basically now explain why there is lots of galaxy formation by redshift 3. Do I put it on? No. Okay. So some theorists said this, but there are famous stories in astronomy about theorists telling experimentalists that they shouldn't look, and then the experiments walking out of their office and just going to look.
Really?
Right. Yeah. So, yeah.
Well, there's a standard description of the theoretical astronomers that they're.
Go ahead, say it.
Often incorrect, but never uncertain.
There we go.
Yeah. What is this?
Question over here. Are you done with that?
Yep.
That was a good question. How about up here? Way up back there at the... Laura, you got a mic? Oh, you got to get this back to Laura. Your thing should work fine. Just keep your hands in your pockets.
Why doesn't it happen? It's a Boston conspiracy. This doesn't happen in other towns.
When you said a few minutes ago that we had wrapped up the structure of ordinary matter, does that mean there's some fundamental reason why you wouldn't see at a higher energy or smaller length scale some particles, another level of particles smaller than quarks?
Good.
No, you could see substructure within quarks in principle, but it's a profound result of quantum mechanics that to excite internal structure, you have to deposit a finite amount of energy, which in the case of quarks, we now know experimentally is quite large. So, and if you don't deposit that much energy, you don't see the internal structure. So for all processes that don't involve the requisite enormous amount of energy, the theory we have is perfectly adequate. And quantum mechanics protects us from the uncertainties.
How about a question?
That's why we have to go to great lengths, like these powerful accelerators, in order to get beyond our description. It's sort of self-protective. And that's a profound aspect of quantum mechanics.
Going right here.
String theory has enjoyed a lot of popularity.
I'm not sure if you're on. Put it right in your chest.
String theory has enjoyed a lot of popularity in recent years. But my question is, what is the current level of experimental evidence that actually supports it?
Very good. Isn't that yours?
There isn't any. I mean, it's
Next question.
Well, it wouldn't be fair to leave it at that.
Right.
It's a work in. I mean, the theory is a work in progress, and it does have many attractive features, and suggests possible phenomena. But unfortunately, we run into the problem that just came up in discussing why I think we have something like a final understanding of ordinary matter, which is that what string theory is about, probably, is structure on extremely, extremely small distance scales. That's inferred from the consistency of quantum mechanics and gravity by a variety of indirect arguments. And quantum mechanics has this property of hiding those things, hiding those internal structures very well until you deposit enough energy. So it's going to take either a lot of luck or enormous ingenuity to extract testable consequences from ideas about really, really tiny, really, 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 really tiny substructure within
20
matter.
orders of magnitude.
Yeah.
Smaller.
Now, but it's not entirely. I mean, I showed you some of the indications that you can construct sort of from the bottom up that unification takes place. What I didn't show you is what the unified theory is. And at present, the only really conceptually consistent theory of unification, including gravity, is the string theory.
How about a question in this theory here?
But most of the consequences...
Laura, where are you?
Yeah.
How about right over there? There's a young man over here, in the back, in the bleachers. There, yes. Okay, hold on now. This is going to be a dynamite question.
Whoa. And is this on?
Yes.
Okay. What I was wondering is about the conspiracy.
Yes.
Isn't it just that there weren't any complex life forms around to see the ones that didn't work for complex forms?
Well, that's the selective theory, which may very well be true. But and perhaps is becoming the majority opinion, but I don't know if it's there yet. But in any case, it's under debate. But you should realize that there are some enormous assumptions that go into that. The first assumption is that the part of the universe we've seen so far, which is remarkably uniform in its properties, that is, the same laws seem to hold everywhere. You have the same value of the electron mass, the same value of the proton mass, the same equations govern stars as far away as we can see, and we can study their spectral lines and really see that they work the same way. You have to say that that's all because we just haven't looked far enough yet. And eventually, if you looked far enough, you would see something quite different.
But we're nearly
Because
at the limits.
there are many universes, so to speak, to choose from. If you could establish that framework, then this argument by selection would make sense. But the more traditional ideal that Einstein espoused is that the reason we've only seen one set of laws is that there really is only one set of laws, and we have to understand it not on the basis of selection, but on the basis of consistency or symmetry or some dynamics yet to be discovered, some profound unified theory that would just explain it all. That may still be possible, but what seems to be happening is that we're understanding things better and better, and these conspiracies still look like conspiracies. They look more like conspiracies than ever, and so the selective alternative is becoming more attractive. On top of that, we now have the inflationary model of cosmology, which could explain why big patches of the universe are uniform, even though the universe on the very largest scales might be far from uniform, because the initial thing was inhomogeneous but blew up by an enormous factor with inflation, and so little homogeneous pieces got really big, but on the very largest scales, things aren't homogeneous.
Let's go over here somewhere. Sherry, do you have somebody over here? How about this gentleman down here in the front? And then maybe we'll try to get this person over here. Where's Laura? Oh, you're hiding. I can't see. The right fellows are so humble.
Thank you.
Please.
I recognize that when I look up on a clear day and see the sun, I recognize that there's a tremendous amount of matter in photons, energy, and plasma that is radiated from our sun. And now, with all the hundreds of millions of galaxies, and we look into deep space, and we see those photons that have been traveling for those millions of years, there must be a tremendous amount of matter and energy traveling in that space at 186,000 miles per second. Have we accounted for that matter yet?
That energy.
And energy?
Photons is energy.
Yeah, I think you're talking about the background radiations, which are reasonably well understood from X-rays, etc., down to radio. There's a still some slight uncertainty about the nature of the infrared background, but that should be resolved with these Spitzer observations. Yeah. But I think that so the energy density of those background radiation fields.
That turns out to be about a part in 10,000 of the energy in the universe.
Right, very small.
Yeah.
One component that isn't yet understood is the gravitational waves.
Oh. Yes.
Well, a number of years ago, the Super Collider was canceled. Now, this new accelerator is going to be being built in CERN. Will it have the same capability or greater capability than the Super Collider? And by the way, why was it canceled? Was there any scientific reason for it?
Answer the first question.
The CERN Collider will have roughly the same capabilities as the SSC would have. The SSC actually would have gone to some slightly higher energies.
But I think it's true, is it not, that in terms of time, at CERN you're roughly now, or at Fermilab, about 10 to the minus 10 seconds after the Big Bang, simulation. But the SSC would have pushed you back in time only 2 orders of magnitude to about 10 to the minus 12 seconds. And yet to really address some of the fundamental issues that we need to address, we need to get back to 10 to the minus 35, 10 to the minus 43, Planck time. Orders and orders and orders of magnitude.
Yeah, well, that's not going to happen.
Not so we
have to use our noodles.
There you go. Thank you. Instead of the person over here, Laura, please.
Yeah.
I mean Sherry. Sorry. And then the person over there to your left, Laura.
I was wondering, how likely is the Big Crunch? Why, since everything's accelerating away from each other, how likely is it for it to actually come back together again?
He knows the answer to that.
Yeah, I think the answer is right now it's not very likely because of the results from WMap, etc., which indicate that will not happen.
Right.
Yeah.
Not to worry.
Worse things can happen, of course.
But there are lots of little crunches, usually.
Yeah, yeah.
There are black holes all over the place.
Yeah.
But the universe as a whole is probably not a black hole.
Moving out forevermore.
Yeah.
Person up here?
Yes.
Oh, hi.
I have actually a set of 2 questions. First is, what do you think about alternatives of dark matter, like Mond theories or other, and that just modify mathematically the equations for the potential? And the second is, it's general understanding that higher levels of complexity should be described by different sets of rules, emergent rules. Is it possible to have some like unified set of rules that will go all the way down to the quarks that will be able to deduce everything or not? Thank you.
Okay, so these are 2 very different questions. The first question is, are there other ideas about the dark matter other than supersymmetry that are plausible? And actually, my favorite idea about dark matter is not the supersymmetric idea at all, but another kind of stuff called axions that I named after a detergent, actually. Well, it's another story, but that's so there are, that to me is the main competitor. I also now think it's possible that there's some of each. That would have seemed very unlikely to me a few years ago, but now I think there are reasons to think that it's not crazy that they should come out. It wouldn't require a tremendous conspiracy for them to come out roughly equal. Or rather, it's a conspiracy we can explain. Then there are other alternatives. You mentioned Mond that, well, there's sort of a class of alternatives, a broad class which superficially sounds very attractive, which is to say, maybe it's not a new form of matter at all, since you've only detected it gravitationally. Maybe it's that you were using the wrong equations for gravity.
Right.
And that seems like a very plausible idea superficially, and it was certainly an idea that many people were tempted to explore. However, when you work out the equations, you find that it's very difficult. Well, let me put it this way. It's hard to say something is impossible, but all the attempts to modify gravity have, first of all, been very ugly, and secondly, have not really given a consistent theory that fits the observations. So I think the accumulated experience of mankind is very much against those ideas, especially since we have relatively conventional ideas that do the job. For dark energy, it's different. It's conceivable, I think, that we really will need to modify our theory of gravity in a profound way to take into account the dark energy. And it's conceivable that on really, really large scales, gravity is different. And the dark energy should be considered as an aspect of gravity as opposed to a new form of matter.
What about the other?
Oh, and the other question was about emergent phenomena.
Whether there's a common principle that will apply to emergence up and down the scale.
Well, whether there's a common principle that applies to emergence up and down the scale. Well, there's one principle which is that the universe can be analyzed. What we found is that, there's one really profound principle. There are several profound principles, but I think the most profound principles that make the analysis of emergence and understanding how the rich phenomena that we observe in the world at all scales can emerge from simple laws at small scales, how that happens. I think the two most profound aspects of it are, first, the locality of physical laws. That is, that the interactions are basically there are simple interactions between things at short distances, and very little influence from things far away. Astrology could have been right logically, but it just doesn't happen to be right in the world, and that's fortunate because it means we can build up our description a step at a time. And the other aspect is what I've already alluded to a couple of times, quantum mechanics, which shields the complexity of lower levels and allows you to encapsulate your description of one level to build up to the next level. So those are two profound principles that I think rationalize Wigner's great paradox, the unreasonable effectiveness of mathematics in understanding the world. I don't think it's unreasonable. It's just that the laws happen to be such that they allow this kind of systematic analysis because they're local and because they shield complexity as you go up.
We're running a little late, so we'll take perhaps one more query. Who has a query that would be applicable to both speakers? So they could both have a crack at this final. Are you sure you're applicable to both? All right, this young man over here.
Thank you. You mentioned explicitly a cosmological constant, and I know that from what I've read that Einstein initially introduced it because he was unwilling to accept an expanding universe at a constant velocity. Now I've read that it's been incorporated again because of the accelerating expansion of the universe. So how do you believe that it's a way of just normalizing the equations that we have until we discover something better, or is it really something that's a fundamental part of the universe itself?
You want to try that, Colin?
Well, you mentioned the cosmological constant. That's a very special case. There may be much more structure to that cosmological constant and much more detail in terms of understanding how that evolves with time. And one thing it would affect is the equation of state, which was shown, the relationship between pressure and energy density as a function of time, so that at least they're relatively simple. I mean, I'm talking about simple in inverted commas, experiments that can be done to at least have a look at any possible variation of that constant with time and any possible variation of the so-called equation of state with time. And these will be done, these experiments can be done over the next 20 years or so.
But as a leading astrophysicist, do you have a physically intuitive feel for the cosmological constant, other than a useful mathematical crutch?
No, I was extremely skeptical about it because it has come and gone, every decade of my scientific life. And it's back, and there seems to be much more there than there was before. But I really think that it's just a kind of a minimal understanding at the moment.
We'll give Frank a final crack at that cosmological question.
Yeah, well, just to make it clear, the cosmological constant is the same thing as what we've been calling dark energy, and it's the same thing as empty space weighing a little bit. To me, the really profound question is not why it weighs a little bit, but why it weighs a little bit instead of what it should weigh, which is an enormous amount. That indicates, we definitely know that there's this structure in empty space with quantum fluctuations, with various so-called Higgs fields and quark-anti-quark condensates. Just a lot of complexity. And gravity weighs this all. And yet there has to be other things that cancel off almost all that weight. So I think we're at a primitive stage in understanding the balance of these different contributions to the weight of empty space, some positive and some negative, and a great task that's probably going to take decades, at least, is to identify all these different contributions and understand how they interplay and take it apart. And it won't just appear as one number. It'll appear as a whole rich story of structure. It's a great task for the future to understand it. I think we're in very, very early days of that task.
So next week we'll be moving further along the arrow of time with experts on stars and planets. And before we leave tonight, we should thank Colin and Frank one more time for some wonderful talk.